But most of the algorithm we'll be looking at will be iterative algorithm. That means there's a certain time index. We usually use K or T to index the time. Sometimes it's discrete, sometimes it's continuous. Most likely will be discrete for what we'll be looking at. Okay, so I have to index this, and we hope that as time goes on, as this index K or T becomes very large, something good will happen. For example, the algorithm actually stops. It converges. It converges at a pretty good point, solving some optimization or gain problem. All right, so that's enough background of just this one line here, an iterative distributed algorithm. So what is the algorithm? Let me write down the algorithm first. It's so simple to write down. It's just one single line, and then let's intuitively look at it before moving on to mathematical analysis of it. So what's the algorithm? Pretend that you are the transmitter of pair I. Okay, there are many logical pairs. This is you, your intended recipient. And the intended recipient will measure the SIR all the time. Let's say discrete time, time t. And then it will feed this back to you. Okay? And then this feedback received at the transmitter will provide all the hint that you need to know. You do not need to know anything else about this whole network. Because what you'd be doing is to say, all right, I got a target SIR, gamma I. That's fixed. It doesn't vary over time. And then I got my current received SIR, which varies over time because I change my power and others change their powers. I look at a ratio. Okay, gamma I divided by SIR at time t. And I say, this is my gain parameter. I'm going to multiply my current transmit power at time t by this ratio. And that will be my transmit power at the next discrete time t plus 1. And this is true for all the pairs I. So we use this notation, all I. And that's it. This is DPC. Say, wow, that's pretty simple. Well, it's actually very simple. Okay, how simple is it? Well, let's take a look.